Hi, nice to see everybody here. Glad you all came. Okay, let's see. So my talk today is titled Why Security Data Science Matters and How It's Different, Pitfalls and Promises of Data Science-Based Breach Detection and Threat Intelligence. So this is going to be a two-part talk. So the first 50 minutes of the talk are going to be sort of very broad and general, and I'm going to talk about what data science is and some unique problems that come up when you apply data science to security problems. And then so that's going to take up 50 minutes, and then there's going to be a 20-minute break. And the second part of the talk, I'm going to talk about some like 3 different projects that we've done in my group at Invincia. So that's going to be a more technical part of the talk. And I'm going to hopefully inspire you and show you some interesting applications of machine learning and data visualization to computer security problems. So I just want to call out that a lot of the work I'm presenting in my talk was done by me, but also by other members of my group. So Alex Long, who's actually here in the audience, David Slater, Giacomo Bergamo, Constantine Berlin, and Robert Gove. So thanks to them for all their contributions. I'll be calling them out throughout the talk actually in terms of areas where they've contributed to the work that I'm going to present. Okay, so just quickly to give you some context for like who I am and the organization I work for. So I work for Invincia. Has anybody out there heard of Invincia? Sounds like some people. Okay, so most people who know Invincia think of us as a commercial computer security company. We also, and so the majority of people who work for Invincia work for that side of the company. I work for an organization within Invincia called Invincia Labs that has about 40 researchers divided into a few different teams that do different security related research. My group is 8 people, and we do machine learning and data visualization and data storage research applied to security. Okay, so again, so the first part of the presentation, I'm going to go over sort of what data science is at a pretty general level. Hopefully everybody can get something out of what I have to say. I know we have probably a very diverse group here. And introduce machine learning and data visualization, and then talk about some unique issues that come up when you apply data science to security. And then I'm going to go over the case studies in the second section. I already said that. Okay, so we can just get into it. So what is data science? They're really, so at a high level, there are 3 sort of skill areas that you need to be a data scientist. So you need to know how to store data at scale. So that requires like a really sort of diverse knowledge of a diverse set of databases and data storage technologies. You need to know how to analyze data. So you need to know about machine learning. You need to know about computational statistics and old school statistics. Then you need to be able to explain your results to others and also to yourself, right? You need to know how to visualize data. To actually explain complex math to managers, and also to make sense of data sets before you start building models to analyze them. There's a huge range. So data science is not just a security thing, obviously, right? It's a growing field. It's become a big deal in a lot of different areas. So there have been recent breakthroughs in computer vision using data science methods. Obviously voice recognition, social network analysis, robotics, these are all fields in which people use, they have big data storage problems, they have machine learning problems, and oftentimes there are visualization problems as well. So when you do data science and security, you benefit from the work that's being done in these other fields as well. There's a lot of applicability of work done in, say, in computer vision and natural language processing to computer security data science. Actually, let's see, how does this, oh, there we go. So like sorry, technical difficulties. There we go. Okay, so most data science projects that we do in my group involve all 3 areas of data science. So this is just an example prototype that we built a few years ago, where our problem was we had all these security alerts coming from our product, from our customers' networks, coming to our system, and we wanted some way to make sense of like the thousands and tens of thousands of security alerts we were seeing. So we were asked to build a clustering system, so a system that identifies similar groups of events, so that an analyst, when they're looking at security alerts, doesn't have to just look at one alert at a time, right? But can look at groups of alerts that share common attributes. So in this prototype, right, in this visualization, you're seeing each one of these balls represents an individual security alert, and the balls are close together as a function of how similar they are, right? And so what we find is that when we cluster events in this way, we can dramatically speed up our comprehension of what's going on the network, right? Because we don't have to go through 1,000 alerts by themselves. We can go through like 100 clusters, and we can characterize the clusters as opposed to an individual alert. So when we find an interesting cluster, we can drill in. So just a simple example of a case where we had to figure out how to store the data. We had to figure out a machine learning method for identifying the clusters, and then we had to come up with a visualization that was compelling, that made people see the benefits of clustering and allowed an analyst to actually look at alerts. Okay, so why does security need data science? Right, there's lots of skill areas in security, like vulnerability research and you know, like network administration and all other skill areas that aren't clearly not necessarily data science areas, right? Like why can we benefit as security practitioners from data science approaches? So I think that sort of the big point one of the big points I want to get across in this talk is that well, I want to make the point that data science is really important to doing security, and particularly doing detection. And so sort of the way I see it is like, you know, there are advanced adversaries breaking into our networks, and there's lots of talk about the need to collect more data. I actually suspect that in many cases we already have the data that we need to detect the adversaries. We just don't know how to analyze the data, right? So there are people who do like full, you know, like organizations that are serious about security do like full packet capture, right? They're tracking every packet that's across their network and over some window of time, right? People use SIMs to aggregate huge amounts of log data. Most of these data, I would argue, are never really fully exploited for detection purposes. I mean, it's because like human analysts who are sort of manually going through the data are just never going to be able to take advantage of all that data, right? What we really need are automated algorithms that can look at that data and reason in an intelligent way about it. So it's not just humans sort of picking through the data and looking for a needle in the haystack. So we have intelligent support. So right, there are a bunch of different types of data that we can take advantage of. I guess I talked about the logs. There's also, you know, this user behavioral data, and then there's also, from a threat intelligence perspective, there's just this huge volume of malware that we are collecting as a community, right? So the latest stats that I found on avtest.org, which is a nonprofit that tracks malware, are that there have been 400 million, since the inception of the internet, there have been 400 million unique malware samples that have been observed, right? And so I would guess that like a tiny fraction of those malware samples have ever been reverse engineered. And so hiding in that huge pile of malware could be the next Stuxnet, right? But we don't know that because we don't have tools to go through it. So some of the work I'm going to talk about in this talk has to do with automatically reverse engineering malware to extract intelligence using machine learning techniques. Okay, so there's been a lot of talk about data science and security for a while, and I think it's natural. And there's some cynics, right, who say you know X, Y, or Z anomaly detector has no chance of working. So we've seen that all before, right? But I think I would argue that I think there aren't good reasons to be cynical, actually, because if we look at other domains in which people are applying data science to hard problems, let's say like speech recognition, we've really crossed a threshold in the last few years between machine learning approaches that say try to transcribe, translate between speech and like spoken language and text. We've seen breakthroughs against those kinds of problems, and all of a sudden systems that like approaches that weren't usable or problems that seemed intractable in years past have now been solved to the point that we now have speech recognition technologies that we're using on a daily basis, right? So this chart is just a summary of a number of systems over the years that have taken on this sort of speech recognition challenge. So this TIMIT data set is a baseline sort of validation data set against speech recognition algorithms. And basically what this chart shows is that speech recognition systems have just incrementally gotten better and better over the years to the point where we've reduced the error a lot, right? So in 1998, right, if the average error rate was 24%, right, now we're down to 18%, and somehow that seems to be a crucial transition, right? Where now we have things like Siri, which actually seem to work pretty well. At least I use those kinds of technologies. And we've seen probably an even more dramatic increase in our ability to recognize objects and images using machine learning techniques. So this is a chart. This is a similar chart, right? That's showing how well object recognition systems did that use machine learning approaches at recognizing objects and images from 2010 to 2015. And we can see, so in 2010, the average error rate was like almost 30%, right? And we've seen it drop just in the last, in like 5 years, right? Down to an error rate of less than 10%, to the point where it's pretty incredible what computer vision algorithms can do now. So I think my sort of provocation here is if data scientists have been able to make those kinds of breakthroughs, like really qualitative breakthroughs that have enabled new kinds of technologies in other application areas of data science, it seems quite is it possible that data science could produce really game-changing technologies in computer security? And I think that is the case, and hopefully I'll convince you that there's hope there in this talk. Okay, so that was sort of the high level part of the talk. Now I'm going to go into more technical depth and introduce some basic machine learning ideas. So for people who have a background in machine learning, this may seem basic, and for people who don't, this may seem sort of difficult and dry. So bear with me, and please ask questions if anything is confusing in what I'm about to say. Okay, so I'm going to start with just lay the groundwork with some definitions. Okay, so there's this idea of training data in machine learning. So that's the data that you give to a machine learning algorithm so that it might learn from the data. So for example, if you're training a machine learning model to distinguish between images of cats and dogs, right? The training data are the images of the cats and dogs. Now there's a distinction between labeled training data and unlabeled training data. So labeled training data are data that you give to a machine learning model, and where you give it a label, right? So if you were given the cats and dogs problem, right, you would show the algorithm images, and you would say that here's an image and this is a cat, right? Here's an image and this is a dog, and that second part that this is a cat or this is a dog is the label. Then there are other machine learning algorithms that take unlabeled training data. So in this case, you would taking again the cats and dogs analogy, you would show a machine learning model a bunch of images, but maybe you don't know if they're cats and dogs for some reason, right? And in any case, you don't tell the machine learning algorithm if they're cats and dogs. You just expect it to do something useful with what it learns, right? Maybe it learns what a cat or a dog is on its own. So that's a more challenging problem, but there are lots of machine learning algorithms that work in that way also. Then there's this idea of test data. So test data is the data that you show to the machine learning algorithm after you've trained it, that you haven't trained it on, that you ask it to make some useful inference about, right? So in the cats and dogs example, you showed a bunch of cats, showed a bunch of dogs, then you show it some new image and you ask it, is it a cat or a dog, or is it none of the above, right? And that would be the test data. So it's called test data because people use that data to evaluate how well the machine learning system is actually doing in terms of its actual learning process. So there are two, so I sort of already suggested this, but there are two big categories of machine learning algorithms. There are supervised algorithms that require labeled training data, and there are unsupervised algorithms that don't require labeled training data. Okay. So then there's this idea of a feature space. This is a bit more abstract. So I'm going to try to make it concrete and give an example. So suppose you have like a directory full of malicious files that have been recovered in some sort of incident, some sort of security incident. And so let's say we know they're malicious, and we want to analyze them using machine learning. So we would pull out so to use machine learning on those files, we would pull out what are called features of those files. And this is a toy example, so suppose those features are just file size and file compression level. So here we have two features, right? File size, file compression level, and the feature space is comprised of those two features, right? File size and file compression level. And so we could also say this is a two-dimensional feature space, in the sense that you could plot those data on a two-dimensional graph, right? And they would each have each of the data point, each of the files would have a position in that two-dimensional space, right? And then once we have that space, right, and it's very useful if you start to do machine learning, you immediately start to think in sort of geometric terms. You can start to think about analyses we can do, right? So it's pretty clear there are two clusters here, right? So we could apply clustering algorithms to identify, there are two clusters of data, and perhaps these malicious files come from two different malware lineages or two different adversary groups, right? So clustering, so why does clustering matter? So for example, to take the example from earlier, right, it matters because it reduces the workload on the actual analyst, right? It automatically summarizes the data that we're looking at. There's lots of other applications of clustering, right? If you have, let's say you want to inspect all the network traffic on your network in a current day, right? You can, instead of looking at each individual net flow, right, maybe you would cluster the flows together, right? So that you could summarize them. And basically, like clustering is useful in looking at large data sets and summarizing them and analyzing them more quickly. And I'll be going over some examples of clustering that we've done further on in the talk. Okay, so sort of similar to clustering is this idea of classification, right? But so clustering is an unsupervised algorithm. You don't need to tell a clustering algorithm what kinds of data it's looking at in order to have the clustering algorithm identify clusters, right? In the case of classification, it is a. Are you guys hearing feedback on the mic, by the way? Or is it just me? I don't know. Yeah? Okay. I'll try moving it. Okay. Can everybody still hear me? Well, I can still hear the feedback, but okay, I'll just try to ignore it. Okay, so in the case of classification, right, so classification is like the example of the cats versus dogs thing, or to make it more security relevant, like malware versus benign ware, right? So you could train a machine learning classifier that does classification, right, on a bunch of malicious files, and a bunch of benign files, and teach it to recognize the difference, right? So in this case, like, you know, if you wanted to distinguish between group A, which let's say is from malware family 1, right, and group B, which is from malware family 2, you would, the task of a classification algorithm, in this case, this is called a linear classifier, would be to identify a line, right, through this feature space, that basically gives you a rule for deciding which family a new file is from. So if we saw this new red file, right, because it's on this side of the line, it would be classified as from family 1, right? That's the basic idea. This all sounds sort of boring. It's going to get more exciting later when I show actual applications of these ideas. So let's look. So say we have. So let me show you guys an example of like a real world classifier. This is a neural network that it's thanks to Andrej Karpathy, who's a machine learning researcher at Stanford, wrote the software. I just spun it up and trained a neural network using his software. So basically, if we have a bunch of training points, like let's say these green points and these red points, right? We can show them to the neural network and ask it to identify a decision boundary such that if we saw a new point, it could make a decision about if that point should be colored green or red, right? So in this case, like maybe the data has this sort of circular shape, like you have this green class and it's sort of in this blob here, and we have these sort of red points out here. It's sort of amazing to watch the neural network adapt to different kinds of data, right? So I mean, I can arrange the data in a spiral, right? And within a few seconds, the neural network learns, oh, here's a good decision boundary, right? This is a good rule for deciding whether or not a new point should be classified as green or red, right? Or we can give it the blob, or we can give it this other kind of wonky shape, right? Or near the end here, I give it a really weird shape. Like this kind of thing, right? And then it's sort of like an amoeba, right? The neural network sort of learns, oh, this is where in general the sort of green stuff is, and this is where the red stuff is. This is all going to seem much more useful later when I show that we've built out of a neural network a very effective malware detector that beats antivirus and works at a very low false positive rate. But in a two-dimensional space, this is how a neural network sort of looks. So why does classification matter, right? So the classic example in security is detecting good versus bad, right? Good files versus bad files, right? Good network streams versus bad network streams. There's other cases like later I'm going to show an example of like an automatic reversing example. So detecting like does this malware sample implement screen grabbing, right? That's another kind of classifier you can build using a machine learning method. Then finally there's regression. So regression is about predicting a continuous value. So like the classic example of like probably where if anybody's dealt with regression, probably dealt with it with sort of like time series analysis. You know, so you can, so like regression models are used to like predict the stock market, for example. You know, so given past performance of Apple stock, like predict Apple's, yeah. Okay. Okay. I don't want to talk too loud until it's turned on. Okay. Yeah. Okay. I'll just keep talking. Yeah, so regression is about predicting a continuous value. So oftentimes we use regression for forecasting. So again, like later in the talk, I'm going to talk about a regression model that we built in my group at Invincia to predict like for a given malware's like given a malware family's history, like say to like Zeus or Storm or Citadel's history, any of these sort of like celebrity malware families, can we predict how many examples of like how successful that family will be in the future, right? That's an example of how we can use regression in security. Okay, so I've been giving these two-dimensional examples, like you know that are obviously not very useful, like file size versus file compression. In fact, right, like machine learning algorithms work in very high-dimensional spaces. So just to sort of prime your minds to thinking about that. Imagine in our file example, right? We used file compression as a feature that we wanted to look at with files, file size as a feature. But then also wanted to add like the first time the file had been seen, like a timestamp or something along this z-axis, right? Now all of a sudden we have a three-dimensional space, and if we want to learn a decision rule about like whether or not, say, a file is good or bad or that kind of thing, we'd have to identify a plane, right? That would define a rule that would say, well, if you're on this side of the plane, you know, you belong in the blue class, right? If you're on that side of the plane, you belong in the red class. So that gives some intuition about reasoning about 3 dimensions. In reality, when we build real world machine learning models, we use millions of dimensions, right? So even like start imagining 10 dimensions, right? And identifying a plane in 10 dimensions that separates 2 types of data, right? So this is actually a visualization of a 10-dimensional cube, right? Probably best looked at on mushrooms or something like that. so if we could really, so we can't really visualize a 10-dimensional cube on a 2-dimensional screen, right? But if we could, every one of the angles in this image would be 90 degrees, right? And they're clearly not 90 degrees, so there's a lot of like distortion going on, right? And every one of the lines would be equal length, right? But so when you start doing machine learning, you start thinking in these high-dimensional spaces, and it's hard to do, right? But that's really the best way of thinking about machine learning is as having a high-dimensional feature space in which we're learning boundaries around the classes that we're trying to identify, right? Right. Okay. Right. I just said this, right? But so it's sort of this mind-blowing thing, you know, when you have to start thinking about these high-dimensional models. But in the rest of the talk, I'm going to be talking about high-dimensional models. So, okay. Are there questions up to this point? Because that's the sort of the end of the machine learning introduction. Yeah. Yeah, so for that we used an algorithm that computes the similarity between every pair of events, and then computes this big similarity. So it's called a similarity matrix. But and yeah, exactly. Yeah, cool. Other questions? Yeah. Yeah, so we use most of the tools we use in thank you. Okay, so the question was what tools we're using to build the experiments or the prototypes that I've shown so far. So we use Python. We use the sort of scientific computing ecology around Python. So there's a library called sklearn. We use a lot as an open source. It's probably the best, I would say, Python open source machine learning library. And we use D3, JavaScript, those kinds of things to do visualization. Actually, the visualization you saw was in Flash. This was a couple of years ago, so back when Flash was still a thing. But yeah, but we use whatever we need to usually. But usually it's sort of we use Python and NumPy, SciPy, sklearn, that kind of thing. Yeah, question. Yeah, so that. You mean in the case? Oh, the question. Thanks. Yeah. So he asked what clustering algorithm did we use? Yeah. So the algorithm you saw. So I guess I misspoke when I said that we used the clustering algorithm. Actually, all we did was compute the similarity matrix, reduce the dimensionality, and visualize it. And what pops out are clusters visually, right? So there was no clustering algorithm used in that case. Yeah. Okay. I don't want to. We actually did. I'm sorry. We looked for connected components in the similarity graph. And then we colored them differently to, so the clusters would pop out. I should probably, just so I can get through the whole talk, I think I'll keep going, and there'll be more opportunities for questions later. Okay, so now I'm going to talk a bit about data visualization. So first I'll show some examples of data visualization, and then I'll talk about some of the theory behind like why data visualization is important. Okay, so has anybody seen this visualization before? No? Okay. Does anybody know what this is of? Who hasn't seen the visualization before? No? Okay. This visualization, so Aaron Koblin is sort of an artist. He's also a good data visualization person. He got this data from the FAA, I think. And so these are sort of flight path data. So they're like latitude and longitude pairs for flights in the US. And then he just plotted them in a 2D space, right? And what pops out is this interesting structure, right? And so immediately I think when you look at the visualization, you get all sorts of stories out of it, right? You can start to think about, well, like where are these hubs, right? Like what's going on down here, right? Is this San Francisco and LA, right? And you start to get a sense of what's going on in terms of the flight data that you can never get if you're just looking at a text file, right? I think that's sort of like the big point of visualization, right? Is that there's really no other way to make sense of the data other than finding some elegant way of throwing it on the screen. And it's usually a pretty simple way. This is sort of a classic. If anybody's read Edward Tufte's books, right? So maybe some people in the audience have seen this visualization before. This is a classic visualization that tells the story of Napoleon's demise in the early 19th century. So the basic idea, right, is that here was where Napoleon's army started. When Napoleon decided, he wanted to invade Russia, so here's where he started on the map, right? And here's the path his army took. The thickness of this line is in proportion to the number of troops he had. Yeah. So he started out he was doing pretty well initially, right? Then his army splits off, and some go sort of die over here. And then the winter comes, and they start dying off, right? And finally he gets to Moscow, right? And his troops have died. There's an order of magnitude less troops, right? Then he starts beating his retreat, right? And this is this black line. By the time he's back, he's screwed. Yeah, like it's over. So you could. I mean, it's hard to find another way of communicating that story, right? I mean, you could write a history book about it. This is a very good. This is a classic example of visualization, right? Where you tell a complex story using very intelligently chosen sort of visual attributes. Then there are visualizations that, so visualizations don't have to be static, right? So there are visualizations that include, has anybody seen this before? This is Gorse, right? So this is a visualization of the evolution of the Python interpreter starting in the early 90s. And so what you're seeing are different developers moving around and adding files to the Python the file hierarchy, right, in Python. And this is another example of telling a complicated story, right, using an elegant visualization. So you're seeing the sort of the birth of Python, and you can keep watching, right, and you can see all the way up to the present. Okay, so why is visualization? So from a more theoretical perspective, why is visualization good? So it really has to do with the data processing capabilities of the human visual cortex, and there's been a bunch of research on this that I'm not an expert in, but hopefully I know enough to talk about in this talk. So if you look at these panels here, right? I think hopefully you guys all have the same experience that I do, which is that the anomalies pop out right away, right? So if I look at this panel, right, I immediately see that there's one data point that's different, right? And it doesn't feel even looking at these small panels, for me it's pretty clear. I'm not doing a brute force linear search, right, to identify the anomaly, which is what maybe a traditional computer algorithm would do, right, which is iterate over all the items and try to figure out which one is different. I mean, the visual cortex processes in parallel, right? And if you present data in the right way, complex patterns pop out. And so that may be less obvious in this example. If you look at something that's more complicated like this, I think you can really see it, right? I mean, if you imagine, hopefully everybody sees the square over here, right? Popping out. So if you imagine writing an algorithm that would identify, so we didn't even, when we looked at this visualization, we didn't even know what to look for, right? I didn't know to look for a square of these plus signs, right? My brain was operating in an unsupervised way, right? It was just looking for interesting structures, and within probably less than a second, right, that structure popped out. Imagine trying to program a computer to identify interesting structures. It would be a very hard programming task, right? But fortunately, we have our visual system which does it automatically. And we call that pre-attentive reasoning. It's before our sort of higher order cognition even sort of kicks in, right? We recognize those kinds of patterns. Of course, that doesn't always happen, right? So here's Where's Waldo. Yeah. So Where's Waldo is it's almost like a hacker created Where's Waldo to force our denial of service our visual system and force us to brute force a visual image. Yeah. And I think part of the pleasure of it is as you're brute forcing it, you're seeing interesting, funny stories pop up. But there's really I'm not sure that there's a much better solution than visual brute force. So this is an example of a bad this would be a poor visualization for the purpose of data analysis, right? You want to find some better way of representing your data. Okay. So there's some design principles that go into visualization. The advisor of one of the guys in my group, Robert Gove, has a mantra. It says overview first, details on demand. This is Ben Schneiderman at University of Maryland. The basic idea there, right, is when you design a visualization, in the case of, I keep going back to this example, there'll be different examples later, but of the clustering visualization, we give an overview, we show all the clusters on the screen, right? And then when you move your mouse over one of the alerts, you get some details, right? So it's useful. So people find that useful, basically, when you do user studies and stuff like that. Okay, and then so visualization should either answer specific questions, right? You should be able to quickly tell somebody what's the trend in my stock portfolio over the last day, right? And be able to really efficiently and specifically answer that question. Or if you're going to make an exploratory visualization, that should be the clear goal, right? And you should make sure that you're actually facilitating that, because a lot of times people do something in between, right, where they're not really sure what the goals of the visualization are, and I think people then take the visualization less seriously. It's important to design with a user in mind, right? So we found this with a lot of our work. So my company is a research company. We're a group of researchers who are somewhat disconnected from practitioners sometimes. So what we found is we need to go out and actually interview the people who are going to be using our tools, understand what their needs are, right, and then go back and like be very disciplined about designing the tool with those people's needs in mind and their skills in mind. So like the visualization you would design for a doctor around like what's going on a hospital floor, right, which is probably very different than the visualization you design for a nurse's aide or that kind of thing, right? In the security space, right, what you design for a malware reverse engineer is different than what you design for like an IT security administrator. Okay, any questions about the visualization stuff? Okay, and oh yeah, please, and I will repeat your question, yeah. Yeah, that's exactly right. That's exactly right. Yeah, and if you can find, so it's pretty magical. Yeah, so I'm sorry. So you said essentially what you're doing when you do visualization is instead of looking over thousands of logs individually, you're projecting them to a screen in order to see them all at once. Yeah. That's right. Yeah. Yeah, so you said instead of having to sort of manually pick through thousands of log entries, you can see them all on one screen. And so I think that's absolutely true. And with an elegantly designed visualization, it can be pretty magical what can happen in terms of your ability to cut through a lot of data all at once. Okay. So I've given a lot of sort of general, a lot of general information about data science, and I've used security examples. But there are really some fundamental differences between the way that you do data science in general, like the way that statisticians are trained or computer scientists are trained to do machine learning, and the way that we have to do data science when we do security. And so I'm going to make an argument for what I think those differences are and what some potential solutions are. So the big difference, right, is the presence of an adversary, or that's a big difference. So like if you're, so like in the hard computer vision problems that people at places like Facebook and Google are trying to solve, that there isn't some adversary behind the scenes trying to like trick the machine learning algorithms into thinking that like an old cat is a young cat, right? Or at least I hope not, right? You know, that's like, there isn't an adversary there trying to trick the machine learning systems. And so that's a big difference. So that's just a big difference. So if you train it, so in one of the ways in which that's a difference is if you train a system to recognize the difference between, let's say, cats and dogs, right? It's likely that system will continue to work over the years and won't degrade very rapidly in terms of performance, right? Probably cats and dogs aren't going to look very different 5 years from now than they look right now, right? That's not the case when you have an adversary that's evolving and trying to defeat your detection mechanisms. In that case, we very much do see that our machine learning models that we build in our group definitely go out of date. And I'll show you guys some examples of that. So this chart is a little bit hard to understand, but I'm going to take some time to explain it. But basically, so here's an example of, so I want to talk about a system that we built over the last year in my group to detect malicious behavior in system logs. So this was a big project. We gathered a huge amount of training data, right? We ran tons of malware in a sandbox, and we also collected data from our Invincia's network and tracked sort of what benign behavior looks like. Then we built this machine learning model that works pretty well at detecting malicious behavior. But then what we found, and so here are our results, right? So at sort of year zero in using this model, so and I can go into more detail about how we did this evaluation if people are interested. But basically, the idea is, so at year zero, when we trained the model on examples of malware and then examples of benign behavior, we were able to detect, so this is the detection rate on the y-axis, and this is the false positive rate on the x-axis. At a roughly zero, as the false positive rate converges on zero, we're able to detect about like 82% of the malicious behavior, right? So that's a useful sensor. I mean, it's not going to detect everything, but it'll detect a lot of stuff along with your other sensors. But then, you know, if we don't continue to train the model, turns out a year later, right, we can only detect at a zero false positive rate, I don't know, what is that, like 75% of the malware, right? And then 2 years later, right, malware has evolved sufficiently that we can only detect 65% of the malware, right? And that's just like totally different than a machine learning system that would be you know, classifying medical images or, you know, classifying objects on Facebook, right, doing facial recognition. It's just a fundamental difference, right? And we find that a lot in our work. And so it's important. So you have to think about that. And when you're evaluating your model accuracy, you need to build in ways of doing either online learning or retraining your model. You need to make sure you're getting new data, right? And you need to keep in mind, you need to track your model's accuracy as it degrades over time, so you're actually aware of how useful your sensor is. So here's another problem that comes up that people are surprised by when they start applying machine learning to security if they've come from another field, right? So it's the false positive problem. And so really the issue here is that the events that we're looking for, and so networks certainly get breached all the time, right? Like breaches are common, like there's a lot of malware out there. But when it comes to like the data we look at on a network, let's say we're looking at all of the executables on a network or something like that. Probably out of, let's say, like we see maybe 10,000 unique executables on our customers' networks, like maybe 10 of those are malicious, right? I mean, it depends on the network, but a tiny fraction are malicious. So the implications of that are that if you have a system that, say, like for every benign binary that it sees, like 1 in 1,000 times, it's going to falsely flag it as malicious. I mean, if there are 10,000 benign binaries, right, you're going to get 10 false positives, right, on those. If you have a 1 in 1,000 false positive rate, and then depending on your detection rate, right, so that'll be 10 false positives, and if you only have 10 malicious binaries and you're only detecting 80% of them, you're actually going to get more false positives than you are true positives in that case, right? Even though statistically your sensor is very, very accurate, right? It's a 1 in 1,000 false positive rate. So we really need to be working at very, very low false positive rates in the security space. Right. So I mean, here's an example that actually calculated out the probabilities, right? So if you have a detection system that has a 75% detection rate but a 0.4% false positive rate, right? When you do the math, you see that 34% of the alarms will be false positives. We assume a 1 in 100 malware to benign-ware ratio. But by the time you get to a 1 in 10,000 malware to benign-ware ratio, so 1 in 10,000 binaries on the network are actually malicious, 98% of the alarms from that sensor are going to be false positive, and it's basically a useless sensor, right? So this is like enormous, like when you do machine learning based detection, an enormous amount of effort has to be expended on reducing the false positive rate. In lots of other domains, the ratio between the two things that you're looking for is just much more well behaved. It's not so skewed. Okay, I sort of talked about that already. Okay, and then here's another big difference. So there's a need for, in the case of say like a machine learning algorithm that does facial recognition, right? And this is a big research area in machine learning. We don't really care if like why the algorithm thinks that you're looking at a picture of John Doe when it says that you are, right? We just want it to be accurate, right? But in the case of machine learning in a security context, it matters a lot why it said that something bad happened, right? Because if a sensor tells me that like all of the OPM records have been compromised, right? Like I better be seeing some evidence that tells me that's like for sure the case, right? Before I raise the alarm to my superiors and like call in the troops and start whatever, start taking seriously drastic action like shutting things down and that kind of thing. So there's the need to explain. I think in many cases in security data science, there's a need to explain in a very clear way, right? Why when we made a detection, why we think that's actually the case. And so we've built like for example, like in an example image down here that in the second part of the talk I'm going to talk more about this. We've built machine learning systems that explain results to users. So in this case, we built this automatic reverse engineering system. So it detects what functionality exists in a malicious binary. So in this case, it's telling us, oh, this malicious binary captures mouse movement, right? Maybe for some data exfiltration type reason or whatever, user profiling sort of reason, right? And then we say, here's the reason why we think it detects mouse movement, right? It's because it uses these API calls, right? Set cursor position. And furthermore, there are these postings on Stack Overflow in which this API call was mentioned, right, in relation to mouse movements, right? And then the analyst can actually click on the link, right, and go inspect and see like what's the relationship between set cursor position and mouse movement. And I'm going to go into a lot more detail about how that works later. But basically, like there's a need to emphasize explaining your results to analysts in the security space. Here's like, so yeah, this is here. Let me see if I can fast forward. So here's another example of like, so this is another example of a clustering system that we built. But here it's a clustering system not for, it's not a clustering system for security alerts. It's a clustering system for malware itself. So we built this for malware analysts who have to look through hundreds of malware samples a day, right? And the idea was to plot all the malware samples in this 2D space where malware samples that are similar are sort of visually close together, right? So that malware analysts, instead of analyzing all the malware one by one, right, they can look at this, look at the sort of similarities between the malware samples and like identify, oh, here's a family of malware over here, there's a family of malware over there, and then proceed to analyze. But our philosophy in building the tool was that the malware analyst doesn't need to trust us, right, that the malware samples are actually similar. We should show them evidence when they demand it, right, that these samples are actually similar. And so when the analyst selects a group of samples, right, we actually bring up a bunch of attributes of the malware in this panel up here. So here the analyst has selected some samples, and then we're showing behaviors in this color-coded way that the malware samples did when we ran it in a sandbox. So these samples were all run in a sandbox, and then we can see when we highlight them, right, that they all executed similar sequences of behaviors, right? And then if the analyst wants to, they can mouse over these behaviors and get information about what each behavior means. But I think that's sort of, so what we experienced, right, in building that tool is that the actual analysts who evaluated the tool found it, like, I think they probably wouldn't have understood like the math behind like grouping the samples that are similar together. But I think once they saw the visualization and could actually use that to explain to themselves around like, you know, why samples belong together or should be analyzed together, then people used the tool and found it more useful. Okay, and then here's the fourth and last sort of difference I think between doing data science in general versus data science in the security context is the lack of labeled data, right? There are other fields where there's a lack of labeled data, but in a lot of cases, right, we have like nowadays, like in doing computer vision, there are big databases of images that are like tagged, that have been tagged as like, oh, this is an image of a horse, this is an image of a dog, and you can use those labels to train a machine learning system to detect those objects and images. In the case of cybersecurity, it's way different, right? I mean, our adversaries are actively keeping the information that we need to train the machine learning systems away from us, right? We always have to assume that we don't actually have the data that we need to train our models. And so that makes things hard. I mean, there's no doubt about that. So I mean, like a mitigation for that is like the example I showed earlier. Sometimes we can use an auxiliary data source to train a model. So we built a system. We actually presented an earlier version of it 2 years ago here at Black Hat, where we didn't use any malware training data. We trained a machine learning system on Stack Overflow to recognize what combinations of API calls are used to implement like keystroke logging or webcam grabbing or device driver loading. We trained the model on like 6 million Stack Overflow question and answer posts where people talk about how to implement a device driver or a screen grabber. And then we found that when we apply the model to symbols extracted from malware, it actually is accurate in detecting capabilities, right? So you need to use, in security, you need to use tricks like that, right? Because we don't have a lot of reverse engineered examples that we could use to train the machine learning model. So we need to go look for other data sources that they're more reliable and we can obtain in higher volume. Another potential mitigation, right, is just, you know, using unsupervised learning algorithms. So this is just a visualization of the behavioral clustering stuff that I showed earlier, right? But there's lots of machine learning algorithms that don't require that we know what's malware and what's benign in advance. There are anomaly detection algorithms, there are clustering algorithms. So there's a need to look at, like, this is, I think the reason anomaly detection has been so popular in security is because we don't have labeled data. Unfortunately, anomaly detection is very hard to get working right. But anyways, that's another mitigation to the problem of not having a lot of labeled data. Okay, so it's 42 minutes into the talk, and that's all I have. So I was hoping to get some questions and discussion in the last part of the talk. Yeah, so the question was, other than clustering, what other unsupervised learning methods are useful? Yeah, so we find, so clustering is important. There's a class of algorithms called dimensionality reduction algorithms that take a high dimensional space, right, and then try to learn some task like preserve. So in mathematical terms, it's, you know, preserving pairwise distances. So preserving distances between items in the high dimensional space and this lower dimensional space. So we found actually in some of the projects I showed, we were using techniques like that, like in the video I showed. Right. So so here we used a dimensionality reduction technique to take data. So actually each one of those color-coded behaviors forms a dimension in terms of this analysis, and it winds up being some unbounded number of dimensions, like, you know, potentially millions of dimensions. We use an algorithm called principal component analysis to project that data down onto a two-dimensional surface, and it's sort of, I don't know, it's sort of like the shadow of the high dimensional space. So the stuff that's close together in this million dimensional space, right, winds up close together in two dimensional space. And then you can visualize it, right? And it turns out to be, that's often we found that to be very useful, right? And like in this case, it was very useful because the stuff that winds up close together actually turns out to be very similar. So that I would recommend that. I'll leave it at that. Yeah, because there's other questions. Please go ahead. Yeah. Yeah. Yeah, so the question was, given the rare event problem that we talked about, do we run into the curse of dimensionality problem a lot and have to do dimensionality reduction anyways in order to build our classifiers? I think the answer is yes. I mean, we almost always do dimensionality reduction. There's some algorithms that we use, so this is somewhat technical, but there are algorithms like random forests that actually don't suffer from the curse of dimensionality that we found very useful. But yeah, I mean, dimensionality reduction is almost always a key part of our workflow. So yeah. Other questions? Oh yeah, please.
Oh, sorry, another question about dimensionality reduction. I've actually tried it with principal component analysis. One problem I tend to find was that if you have a set of metrics that, say for example, the high values, one set high values.
Yeah.
Sometimes they contradict each other. Like you might have one particular mention, you might have both high value malicious and low value malicious, both having high value. So we might have a high value malicious and another high value malicious, one has positive value, one has negative value. They tend to contradict each other. Did you find that problem, or did you find a way of coming around that problem?
I'm gonna have a hard time summarizing your question. So, and I'm not sure I totally get what you're saying. Maybe let's talk afterwards, yeah? Okay, yeah, I'm sure we can probably get to the bottom of it, but, okay, yeah, yeah.
So describe a workflow where you're presenting your analyst with these clusters based on something like feature vector. How do you prevent them from being biased by the features that they selected if they then use those same features in order to derive the labels that you're going to classify?
Yeah.
Align them to a cluster and present them next to it.
Yeah, okay, so the question was, how do we prevent some sort of confirmation bias in the analysis where, we're showing the analyst features that we use to group things together, but of course they're grouped together based on those features because, that's how the math works. That doesn't mean they're necessarily sort of semantically similar. Yeah, so we solved that problem by using a validation set. So we actually, for the system on this slide, right, we had some malware that was labeled, and we measured how good our system was based on how well we reconstruct the true similarity relationships, given the ground truth that we had. So.
If the clusters are missing features that would allow you to get separation,
Mm-hmm.
give the analyst the wrong case and don't tell them the clusters.
Yeah.
They may be able to give you label information that features are selected for clustering. Saying you're biasing your analyst by only showing them the visual with the already pre-selected features on it.
Yeah.
They're not able to help you bootstrap additional separation.
That makes sense, yeah. So he's making the point that even with a validation set, we may be still biasing the analyst because, well, let's talk about this after, yeah. Okay. I also before everybody leaves, I also want to say, I hope people will stick around for the next part of the talk, which will describe in detail a detection model we built and how we evaluate using deep neural networks, a regression model we built to predict the future success of given malware families, and a conglomeration of visualization tools and analysis tools that automatically reverse engineer malware. Okay, that's just a pitch for the next section of the talk after this 20-minute break. Please, there's a question with the guy at the mic, or, yeah. I think maybe either yell or maybe you have to turn it on or something. Okay.
So you mentioned earlier about visualizations for different roles.
Yeah.
What's the ratio of data modeling to presentation? Is it one machine learning model and multiple presentation?
Yeah. Yeah, so the question was about the ratio in terms of our effort between the sort of the analytics and machine learning and visualization. So it's dependent on the project. So we just did so one of the things I'm going to present about in this next part is on deep neural networks. There the only visualization we did, the colleague and I who I did the project with, was just for our own edification. So we visualized the neurons in the network and all this stuff. But those are like, that we would never present them to anybody but ourselves. They were very ugly and not very explanatory to anybody unless their head was in the problem. So that was like an extreme case with no visualization. Usually it's been about 50-50, I would say. And I think that makes sense because they're both equally important. They're both hard in their own ways. So yeah, it's the best I can do. Yeah. We have time for maybe one more question. Yeah.
So you mentioned.
I'm sorry. So does that mean we have time for 0 questions? Or okay. So should I just take this last one or like? Okay. Yeah. Please go ahead. Yeah.
You mentioned there are often billions of dimensions.
Yeah.
Feature sets, features.
Yeah.
What algorithms do you use to determine which features to include in your model?
Yeah, that's a great question. So the question was, how do we choose which features to include in our model? So there's multiple ways of approaching this, right? One is you keep all your features around, but you use an algorithm to transform the high dimensional space into a lower dimensional space. In that case, you don't throw out any features. That's like somebody mentioned principal component analysis. That's a way of doing that. There are reasons why that is hard when you have a lot of data, but anyways, that's one approach. And then another is, you select features based on, so one, you can do it statistically, right? And so at work, we have lots of debates over how we should do this, right? So you can do it statistically based on how correlated this idea of how correlated your features are with your target variable, right? So if sort of intuitively, I should probably stop talking. So I'll just wrap this up really quickly. So sort of intuitively, it's obvious if like a malware has if a malware is unsigned, right? Like there's no digital signature, that's suspicious, right? But like statistically speaking, like that's semantically suspicious, but statistically speaking, maybe that's correlated with it being malware, right? And so sometimes we use, so you can use simple methods for detecting that correlation and filtering based on that. Sometimes you want to do higher order approaches and stuff like that, but hopefully that gives you some sense of how we do it. So yeah, this is a big topic. Let's talk. I think I'm supposed to wrap up. So thanks to everybody if we can talk after offline. Thanks to everybody who came. I hope you guys come back for the next session. So thanks.